Hi friends, hope you are doing well. I'm Dr. Ganguly. Today we are going to discuss lecture 12 and today I'm going to talk about the Mach meter and also we are going to discuss compressible flow. We are going to discuss some of the isentropic flow relations and express things in terms of the Mach number. So let's begin. So in the previous lecture we discussed the concepts of static and total pressure and we were concerned with incompressible flow. Today I'm going to look at compressible flow. So we'll look at compressible flow and we'll use the Bernoulli's equation between any 2 points, and these points are essentially in isentropic flow, which means that no heat is put in or extracted from this flow here, and also that it is frictionless. So let's assume that the point properties at these two blue points are known. So at the point here it's P1, rho, T1 and V1. So these are the pressure, density, temperature and velocity, and after some time this particle comes to a stop, and when it comes to a stop the velocity becomes 0. The pressure is P0, density is rho 0 and the temperature is T0. So what we are going to do is we are going to try to find relations between P1 and P0, between rho 1 and rho 0, between T1 and T0. So let's do that. So if we consider the Bernoulli's equation for compressible flow, which we derived a few lectures ago, it was gamma by gamma minus 1 P by rho plus V square by 2 equals constant. So I can apply this between these 2 points. So on one side I get gamma by gamma minus 1 P0 by rho 0, because remember the velocity is 0 here, so the term V square by 2 would be simply 0 for the point which has subscript zeros. But for the point which has subscript 1, you get gamma by gamma minus 1 P1 by rho 1 plus V1 squared by 2. Now what we are going to do is we are going to try to express this equation in terms of Mach number. So we start out with the equation I showed in the previous slide, and we can immediately apply the equation of state at point 0 and 1. So remember, equation of state is P equals rho RT. So I apply it here, I get RT0. So what we have done is replaced P0 by rho 0 RT0. Similarly here I get RT1. Now what we do is we essentially divide the left hand side by this entire term, that is by gamma minus 1 RT1. So if we do that, it becomes T0 by T1. The right hand side becomes 1 plus gamma minus 1 by gamma RT1. So essentially this thing gets flipped. That's what happens. And you also have the V1 square by 2 term. Now immediately you realize from the definition of speed of sound or the formulas we derived in previous lecture that gamma RT1 is A1 square, where A1 is the speed of sound at point 1, and therefore I can then express this in terms of Mach number, remembering that M1 would be V1 by A1. So it's the velocity at point 1 divided by the speed of sound at point 1, and the speed of sound is gamma RT1. So I get this equation which essentially links T0 and T1 in terms of the Mach number. So this equation is important and it will be used many times in this course. So essentially now we are talking of compressible flow, isentropic flow. So everything is happening at high speeds. So Mach number is coming into the picture. Now this equation is so important that I have written it out here because you need to commit this to memory, because if you remember this equation about T0 and T1, then you can derive the corresponding equations relating pressure and density, which we will do next. So again, to now start thinking in terms of Mach number instead of velocity, the Mach number here was m1, the Mach number here m0 is simply 0. So essentially the velocity has come to a standstill there. So let's look at pressure, the total and static pressure. Now we already derived the equation in terms of T0 and T1, and now we use the isentropic flow relation. Recall the relation P0 by P1 equals T0 by T1 to to the power gamma by gamma minus 1. And if we use this equation, immediately I can substitute T0 by T1 from here, and I can write this equation here. So now I have a relation between P0 and P1. So essentially remember that P0 is going to be the total pressure and P1 is going to be the static pressure. So essentially all these quantities with the subscript 0, they are the total quantities, and the quantities with the subscript 1 are the static quantities here. Now next equation we look at is density. So what happens to the density between point 1 and this point? So here it is rho 1 and here it has become rho 0. So again we turn to our equation for the ratio of the temperatures T0 by T1, and we use another isentropic flow relation, which was rho 0 by rho 1 equals T0 by T1 to the power 1 by gamma minus 1. And by using this equation, I am immediately able to write this equation here. So all I have done is I have plugged T0 by T1 here. And so I have raised this whole thing to the power 1 by gamma minus 1. So like I mentioned before, in these kind of relationships which involve gamma and powers and so on, you need to have some kind of scientific calculator to do these calculations. We'll revisit this equation in a later class because this is very fundamental for defining what is the point where incompressible flow changes to compressible flow, because that's what we are going to use to look at the density. So does the density remain the same or does the density change? So now with these equations, we try to define the principle behind a device known as the Mach meter. So essentially recall this equation which we obtained before, the P0 by P1 ratio expressed as 1 plus gamma minus 1 by 2 m1 square whole thing to the power gamma by gamma minus 1. Now what I do here is I extract m1 out and write that as an equation. So essentially what we do is we take this gamma by gamma minus 1 to this side, so it becomes P0 by P1 to the power gamma minus 1 by gamma, and we subtract from this 1 and then multiply 2 by gamma minus 1. So essentially this 2 goes up, this gamma minus 1 goes down, and I get this expression for Mach number at point 1. And you can see that this equation can be used to calculate the Mach number at the point the aircraft is flying, provided we know P0 and P1. So we need to know static and total pressure, and then we can use this equation in a device known as the Mach meter to calculate the Mach number at the point where we are flying. Now, talking about Mach number brings us to the definition of true airspeed immediately. So if we want to find the true airspeed, we'll call it V subscript 1. Then we start with the Mach number here, and realizing that Mach number is basically velocity divided by speed of sound, I can write that here. So what would happen is that would be V1 by A1 square, and so I bring the A1 square here and I get this equation here. And also we can do a little bit of rewriting in this term here. So remember, this is nothing but P0 by P1. For example, if I expand this out, I get P0 minus P1 plus P1 divided by P1. So minus P1 and P1 cancels out. So this is essentially identical to P0 by P1. Now the reason I wrote it like this is that often P0 minus P1 is measured in an aircraft, and so if that is available to us, I could plug it in here. But you will see some lacunas, of course, in this equation. The question is, how do I get A1? How do I get P1? And to solve that problem, essentially we turn to something known as calibrated velocity. So just for reference, I have written out the previous equation here, and I posed the question in the previous slide is, how do we get A1 and P1? Remember, they are going to vary with the altitude you're in. So for example, if there is a particular flight vehicle, it is flying a certain height, the A1 and P1 are going to be varying depending on the height concerned, and we may not know these values. So what is done is we use a calibrated value of velocity in many situations. So we call it V subscript cal, and all that has been done here is that the A is replaced by AS, which is the speed of sound at standard sea level, and P1 is replaced by PS, which is again the pressure at standard sea level. So you can remember that this speed of sound at standard sea level is 340.3 meter per second, and the pressure at standard sea level is 1.01325 into 10 to the power Pascal or Newton per meter square. Now, some people use the term atmosphere also. You will hear it used in many books and so on. So, sometime when we talk about 1 atmosphere pressure, we mean essentially this pressure here, 1.01325 into 10 to the power 5 pascals. So you can now see that this Vcal value is easy to calculate because AS and PS are known to us. These are these two values. So if we simply have P0 minus P1 from some measurement, then we can easily calculate this V calibrated because we already know gamma is 1.4 for air, and I'm of course assuming you are flying on planet Earth here. Now, there's one more definition which we should mention before we end this class. We already know that density is varying with the altitude or the height, so we can always write rho is rho h. Now we sometimes define a quantity called equivalent airspeed, and this is defined by equating the dynamic pressure. So we take half rho v square equals half rho s ve square, and so from here I can immediately write ve is v root rho by rho s. So the left hand side is the dynamic pressure at a given height in which the aircraft is flying. So there the density is the general rho. But if we consider the same dynamic pressure at sea level, we put rho s here, then we would get a certain different velocity Ve. So we can easily calculate this Ve because we know rho s is 1.225 kg per meter cube. So today we saw a lot of equations. It's kind of an equation mania out here, but I thought I will put all these in one slide so that you can take a good look at actually what's going on. So what we started with is that there is isentropic flow, it's compressible flow, and at these two blue circles I have drawn, there are these values for the different point properties. So there is P1, rho 1, T1, V1, M1, and here all the subscript zeros are there, and of course we know velocity and Mach number are 0 here because we have got these total properties here. So the equations we got relating temperature are here. T0 by T1 is 1 plus gamma minus 1 by 2 m1 square. So this is the most important equation to remember, and if you remember the isentropic flow relations, you can immediately write the other two equations. So I would suggest you always remember that P0 by P1 is T0 by T1 to the power gamma by gamma minus 1, and rho 0 by rho 1 is T0 by T1 to the power 1 by gamma minus 1. And so if your professor or teacher permits you to take some kind of cheat sheet, you can write these equations in the cheat sheet and you can immediately get the larger equations which are given here. Now from these equations we also got the equation for the Mach number, and the Mach number of course is related to P0 by P1. So if we are able to calculate those quantities, we can immediately calculate the Mach number at the plane where you are flying. So this device is known as the Mach meter. Now we also realized that we can actually have some difficulty in getting this particular value. So instead of getting P0 by P1, we wrote this equation out in a slightly different form. So we get P0 minus P1 by P1. So in this case, P0 minus P1 is measured by some device, for example, the pitot static probe. And then we get this value V1, which is the true airspeed. Now, if you have access to A1 and P1, which are the speed of sound and pressure at the height at which you are flying, you can calculate the true speed. And in some cases or in most cases you don't. So what you do is you substitute those by the standard sea level values. So PS and AS are the pressure and the speed of sound at standard sea level. And then you can immediately calculate V calibrated. So that's the calibrated velocity. So in this equation, you would only need P0 minus P1, which would come from a pitted static probe. And so this equation would act as a kind of virtual sensor of calibrated velocity. Also, we saw that the equivalent velocity can be calculated by equating the two dynamic pressures, the dynamic pressure at the point where you are flying and that at the standard sea level. So these equations are very useful and effective for compressible isentropic flow and useful for many problem situations. So in the last couple of lectures, we have gotten introduced to these ideas such as the static pressure, the total pressure, the dynamic pressure for incompressible and compressible flow. And now we have a variety of equations. So we can use some of these equations to further delve into the difference between incompressible and compressible flow. Now, how do we point out when the flow really starts becoming compressible? The key to that is in looking at the density ratio rho by rho 0 or rho 1 by rho 0, and we are going to do that in the next lecture, which is going to be a short lecture which demarcates incompressible and compressible flow. See you then.